Okay, now let's look at the various different particles that make up the nuclear atom and kind of how we figured out which some of those particles were. All right, so to start understanding the discovery of these subatomic particles, we just looked at the fact that, okay, so ions exist. All right, we know that if we have, some sort of solution and there's just all stuff in it, that we end up getting mobile charge and we can light up our light bulbs and things. This is why they tell you not to stand in a tub of water and use your hair dryer, because tap water has stuff in it. So Dalton's theory didn't take long for it to be challenged. And so this work goes back to the 1820s. And so when we, look at our atom, okay, we started off with just, okay, an atom is just a sphere. But what these experiments started to do was show that, well, maybe inside those atoms there might actually be some smaller parts inside that atom. So one of the first experiments was this Crooke's tube. All right, so a Crooke's tube is also known as a cathode ray tube. Okay, so a cathode ray tube. They beamed these particles. This is how they discovered electrons. So the particles they were beaming through were electrons. So these went in straight lines. They went from the cathode to the anode. And so what they saw was that these particles were negative in charge. So electrons are negative, and that they could be deflected by an electric or a magnetic field. So if I have something that's negative in charge and I bring a negative thing toward it, what am I going to do? I'm going to deflect it away. If I bring a positive thing toward it, I'm going to deflect it toward the positive thing. Okay? They also produced sharp shadows, meaning that these were particles. So this picture I have over to the right, okay, that big shadow there, that's a Maltese cross, a metal Maltese cross that they put in there. And so if they put this metal Maltese cross in there, that stopped the particles, and so the shadow formed. If they folded the Maltese cross down, then the particles would refill that open area. So at this point, what they were able to surmise is what we ended up calling the plum pudding model of the atom, or Thompson's plum pudding model, where an atom was this diffuse sphere of positive charge, and then these electrons were plopped in the middle of it. So we had protons and electrons, but we didn't know that those were called protons yet. We know that now. We just knew that there was positive charge there. And so we thought it was this diffuse sphere, okay? And so plum pudding comes from the fact that this diffuse sphere of positive charge was the pudding, and the electrons that were plopped in there randomly were the plums. So if you've ever had pudding or jello that had stuff suspended in it, that's where they got the idea for this model, okay? Now, when all the positive charges equal the negative charges, you have something that is neutral. When you start to disrupt that equality, though, that's when you end up with ions, okay? And so we can form ions by moving electrons around. So if I have 5 positive charges and 5 negative charges, I'm neutral. But let's say I take an electron away and I have 5 positive charges and 4 negative charges. Well, now that's uneven. Now I have 1 more positive charge than negative charges. And so that's where we get cations from. Okay, so cations have lost electrons. Now they have more positive charges than negative charges. So something like a calcium ion with a +2 charge means that calcium has lost 2 electrons. An iron with a +3 charge means that iron has lost 3 electrons. The opposite is true for anions. Anions are negatively charged. They have gained electrons. And so now they have more electrons than protons. And so a -1 charge means we've gained 1 electron. We have 1 more electron than our positive charges. Okay? A -2 charge. We have 2 more electrons than positive charges. Okay? So that's how we form our ions, is by moving those electrons around. Okay. And so we have this idea that we understand, like, those positive charges are protons. We know that there's these neutral things called neutrons. They have no charge to them. And then we have electrons, okay? We can also put into play where sometimes proton is just P and neutron is just N, but electron is always going to have that minus charge on it, okay? All right. We can also do some really interesting things with mass and conversion factors. So if I know the mass of a single carbon atom is 1.993 times 10 to the negative 23 grams, and I have 12 grams of carbon, I can figure out how many atoms there are. So I can go 12 grams of carbon times one carbon atom for every 1.993 times 10 to the negative 23 grams of carbon. And my grams of carbon cancel. And I end up with 6.02 times 10 to the 23 carbon atoms, which that number is actually going to come into play later and be really important. Okay? All right. So we know electrons exist. We have this diffuse sphere of positive charge. Today, we know that we have these protons and neutrons. So how did we go from Thompson's plum pudding model to understanding the existence of protons? Okay, well, we had this gold foil experiment. This was done by a guy named Rutherford. So there is a source of alpha particles. Okay, so the source had alpha particles. Okay, so these alpha particles were beamed at gold foil. So what they expected was, so let's say I've got my diffuse sphere of positive charge here, and I've got my electrons just plopped in anywhere I want. Okay, and then I have, okay, so there is my plum pudding model. Now, what they expected to see is they expected that as they beamed these alpha particles through, they would either go straight through or they might hit one of these and be deflected slightly. Okay? So this is what they expected to see. Was just major, maybe some minor deflections there. But if we take a look here, those were major deflections. Okay? They deflected at a really sharp angle, which is not what they were expecting to see. Which coincidentally enough is a lot of how science is done is we think we're going to see one thing and then we see something different and then we have to start re-examining, right? And so this led to the discovery that a nucleus existed, that at the center of an atom was a small, very dense thing where most of the mass was contained. And so, again, this is what they expected to see, okay? And this is what they actually saw. And the deflections were not caused by glancing off of an electron, because electrons are really, really tiny. They're much smaller than protons and neutrons. The deflections were from bouncing off of the nucleus. And so this is what led us to the discovery of the nucleus. And then other work was done, and we were able to differentiate protons from neutrons and start to understand that a little bit better. Okay, and so our nuclear model of the atom is that we've got in the center is our nucleus where the protons and the neutrons are contained. And then surrounding the nucleus are our electrons. Okay? Right? So a large portion of an atom is really just empty space. The nucleus does not take up a whole big amount of space. An atom is approximately 10 to the negative 10th meters across. Okay? Now, this 10 to the negative 10th meters can also be written as this, which is an angstrom. You don't see angstroms very often anymore. We used to use angstroms a lot when I was first studying chemistry, but these days I don't see angstrom around very often. But in some older textbooks or some places around online, I still see angstrom every once in a while. So if you see an angstrom, it comes from the diameter of an atom, and it's 10 to the negative 10th meters. Okay, and it has a cool symbol. If you've ever watched Stargate, it's very similar to the Stargate symbol for home. So anyway, center of the atom, that's where relatively all the mass is, and then most of the rest of it's empty space, and electrons are super tiny. Okay, and you can see, our protons and our neutrons have a mass of 10 to the negative 24th grams, but our electrons have a mass of 10 to the negative 28th grams, so 4 orders of magnitude smaller. So electrons are really tiny in comparison to our protons and our neutrons. And so that's why the deflections we saw were from the nucleus, where the protons and neutrons are. And so we can, think about how we look at something. We have a sample of our lithium metal, and our lithium metal then is made up of atoms, and those atoms are made up of, our protons, our neutrons, and our electrons. Okay? And so we went from, early 1800s, an atom was just a sphere. And then, 100 years later, okay, now we've got positive and negative things. And then a few years after that, okay, now the positive stuff's in the center. And then we started figuring out how electrons behave around the nucleus. And then we've continued to discover more. So we've got some basic ideas of how this stuff works, but it actually is fairly complicated what happens inside of an atom and how everything moves around. And so we're actually still discovering. So as we do more work, we'll understand even more.